Hello, I am Dr. Milton Graziano Jr., and I will give a brief description of the results of the work presented in this banner. Before that, I would like to point out that I am affiliated with São Paulo State University, UNESP, Institute of Science and Technology, Sorocaba, Brazil. High-mobility electron field effect transistors were previously developed for high-speed applications, and due to their low noise performance, are currently widely used in small signal amplifiers, power amplifiers, oscillators, and mixers operating at frequencies up to 60 GHz. High-mobility electron field effect transistors are of great interest when applied in radio frequency circuits and analog circuits due to their properties such as high frequency, high electric breakdown field, and high saturation speed. However, adjustments for each application can be made by varying the gate source distance, where applications are typically obtained for various devices such as cell phones, radars, mixers, oscillators, surveillance, reconnaissance, TV transmission, communication satellites, radio base stations, digital radios and attenuators, military applications, and more. This work compares 4 widely used threshold voltage extraction methods in high-mobility electron field effect transistors fabricated at IMEC. Here it is demonstrated that linear extrapolation provides the most robust threshold voltage definition across different geometries and bias conditions. By normalizing drain current by gate voltage curves using VGT, it is shown that the apparent dependence on geometry discrepancies collapses, enabling a clear interpretation of aspect ratio effects under varying drain bias. These results suggest that geometry-dependent trends reported in the literature may partially arise from inconsistencies in VTH extraction, rather than intrinsic device physics. Previous and recent studies report that the extracted threshold voltage in AlGaN GaN HEMTs strongly depends on the extraction method employed. Here, 4 widely used VTH extraction methods are evaluated. The methods adopted are the current method, which calculates the VTH corresponding to the current using the expression drainage current is equal to the channel width times 10 to the power of minus 7, where W is the width and L is the length of the device channel. The second method was the second derivative method, in which the drain current by gate voltage curve is differentiated twice, and the VTH corresponds to the projection of the maximum point of the resulting curve onto the stress axis. The third was the transconductance, divided by the drain current method. The last was threshold extrapolation, in which VTH is determined by linear extrapolation of the drain current by gate voltage curve at the point of maximum transconductance, GM. As shown in Figure 1, linear extrapolation provides the most consistent VTH values across different geometries and bias conditions. Once the extrapolation method is selected, the drain current by gate voltage curves are normalized using VGT, that is, the gate voltage minus the threshold voltage in absolute value, enabling a direct comparison between devices with different geometries. The result of this standardization is shown in Figures 2 and 3. Next, the influence of the aspect ratio on these devices is studied. In Figure 4, the larger L, the smaller its current. However, when the drain voltage increases, the curves tend to overlap. This behavior suggests that the increased lateral electric field at higher drain voltage partially compensates for the current reduction associated with longer channel lengths. Figure 5 shows the curves that consider W, and the higher the W, the higher the current. This result is consistent with the fact that high-mobility electron field effect devices operate with a two-dimensional electron gas. Conclusion. This work demonstrates that the VTH extraction method critically affects the interpretation of geometry-dependent behavior in high-mobility electron field effect transistors. Linear extrapolation provides the most consistent VTH definition, enabling dependable VGT normalization, and avoiding misleading geometry-dependent interpretations that may arise from inconsistent VTH extraction methods.